Let's look at number 88. Researchers dissolved 1.382 grams of impure copper. And so I have some sample here, and the sample is going to contain copper plus other stuff. Then it was treated with nitric acid. And so when we treat it with nitric acid, hopefully the other stuff doesn't react with the nitric acid. And nitric acid only attacks the copper. Nitric acid is an oxidizing acid, and it can dissolve the copper. And so it makes copper 2 nitrate. We end up with. The solution went through a series of steps in which copper 2 nitrate was changed to copper 2 hydroxide. So this was changed to copper 2 hydroxide. They don't tell us how. They just said it goes through some steps. Then to copper 2 oxide. And then to a solution of copper 2 chloride. That was treated in excess soluble phosphates, precipitating all the copper in the original samples, copper 3 oxide, copper 2 phosphate. CO3, PO4, 2. We get that. And so this is the key here. There are a lot of steps, a lot of reactions here. But what they said is this, precipitating all the copper in the original sample. And so what that means is we didn't lose any of the copper. And so, you know, all the copper that was originally here now ends up here. You know, and no other compounds. And so this gives us a mole ratio. We can skip all this other stuff here. And what we can see is that, you know, for every one of these, we're going to have 3 moles. So there are 3 moles of copper for every Cu3PO42. This is the 3. There are 3 coppers for every Cu3PO4 for every 1. So it's a 3-to-1 mole ratio. For every 1 mole of Cu3PO4, we get 3 moles of copper. And so this is a little bit tricky because there's so much stuff going on. So we want to find the percent mass of copper in the original sample. So percent mass, the percent mass is just going to be percent copper is just going to equal the mass of copper over the total mass times 100%. Total mass is given, you know, 1.382 grams. So this is going to be the mass of copper over 1.382 grams total times 100%. Now the mass of copper we're going to get from stoichiometry. So this is stoichiometry. And so that's going to be from grams of copper phosphate. We have this many grams of copper phosphate, copper 2 phosphate. And so we'll go from 2.637 grams of Cu3PO42. And then we'll go to moles. And then we'll go to moles of copper and to grams of copper. And divide that by the total times 100%. And that should give it to us. And so let's see what the book is. So they started with grams of the phosphate, to moles of phosphate, to moles of copper, to grams of copper. And then they take the grams divided by the total grams times 100%, gives you 95.59% copper, and the rest were impurities. The next one. What mass in grams of magnesium nitrate must be used to precipitate must be used to precipitate as magnesium hydroxide, all the hydroxide ion in 50.0 milliliters or 17.0% by mass sodium hydroxide, the density of which is 1.19 grams per milliliter. And so this is more steps to get to the core, you know. Eventually we want moles of sodium hydroxide. So how to get moles of sodium hydroxide? Well, we've got to figure out how to get there, you know. So we have 50 milliliters of this mixture. So we say it's 50.0 milliliters of solution sodium hydroxide. This is not pure sodium hydroxide. This is sodium hydroxide mixture or solution. So 50.0 milliliters solution, but we also have the density of the solution right here. So we could go to grams of solution. And that is, we have 1.19 grams of solution per milliliter of solution. This is sodium hydroxide solution. And then here, if we have the grams of solution, then we know that there's 17.0 grams of pure sodium hydroxide for every 100 grams of solution, sodium hydroxide solution. It gives us grams of sodium hydroxide. Then from there, we just go to moles of sodium hydroxide to, well, wait, no. Yeah, to moles of sodium hydroxide, from moles of sodium hydroxide to moles of magnesium nitrate, moles of magnesium nitrate to grams of magnesium nitrate, and then we're done. Here. If a solution of silver nitrate is added to a second solution containing chloride, bromide, or iodide, the silver ion from the first solution will precipitate all the halide. Silver chloride, silver bromide, silver iodide. If excess silver nitrate is added to a mixture of the bev halides, it will precipitate them all, basically, both or all, as the case may be. A solution contains, okay, so we have a mixture of sodium chloride and sodium bromide. Then they want to know how much silver nitrate we need to precipitate out all the chloride and all the bromide. So this one we do two separate stoichiometries. And so we start off with grams of sodium chloride, go to moles of sodium chloride to moles of silver nitrate to grams of silver nitrate. That's how many grams are required to participate here, react here. Then we do a second problem. We go grams of sodium bromide to moles of sodium bromide, moles of sodium bromide to moles of silver nitrate, and grams of silver nitrate. And then we figure out the total. That is, in this case, we have to add it together. This should be two separate reactions here. It might look like one reaction, but there are two separate reactions here. Be a comma. So this is the sodium chloride reaction here. And so this is gram to mole, mole to mole, mole to gram conversion. That's how many for the first reaction. For the second reaction, how much silver nitrate do we need? So grams of sodium bromide to moles, moles to grams, this many grams, and then combine them. We got to add these two together. For the first reaction, we need this much. For the second reaction, we need this much. For both, we're going to need the combined for both. And so they combine it here, about 1.94. Oddly enough, the backwards problem of this is very interesting. And so number 90, the backwards problem of this is quite interesting. Quite interesting. So when we look at this mixture, let me do it here. What is the percent sodium chloride in the mixture? So the percent sodium chloride in this mixture is 0.230 grams over the total. The total is 0.230 grams plus 0.771 grams times 100%. And so what is the percent sodium chloride in this particular mixture? Bring a calculator. And so, the total is 1.001 grams. (22.97%). 977%. How many sig figs? I'm only allowed 3 sig figs. I went too far. So 22.97% is not. The percent sodium bromide in this mixture is 100 minus that, so minus 100. .02. Since there are only 2 things in this mixture, this is round off error, 97. This should add up to 100%, and this should be 98, and then it'll add up to 100%. But it's all right. I'm only allowed 3 sig figs. Now, the odd thing is this. The amount of silver nitrate that you have to use is unique. This is the amount that's required for 22.977% sodium chloride. If I had a different percent mixture, it gives a unique amount of silver nitrate that we need. That is, which one requires more? I don't know. But if this requires more or less, that means the ratios are different, here. And so let's say, as an example, I had, in other words, I can figure out how many, or what the percentage of the mixture is. So this is a very powerful stoichiometry method. And so let me give it to you here in this sense. And so this plus this gives me 1.001 grams of mixture. And what I'm saying here is the amount of silver nitrate total that you use is unique for each percentage value. If you change the percentage a little bit, it changes the amount of silver nitrate. So if I have more sodium chloride or less sodium chloride, I can tell how much I have based on the amount that I use here. And so let me give you one more example problem of a challenge problem here. So in that last problem, I need 1.94 grams. But let's say I have a new mixture. This is a new mixture here. New mixture. I don't know what the ratio is here. But when I react this with the silver nitrate, let's say this one required 2.31 grams required. And you're going, how can I do the stoichiometry? There are 2 separate reactions here. I'm given the total combined silver nitrate combined. The two separate reactions are this: sodium chloride plus silver nitrate yields silver chloride plus sodium nitrate. This is a double replacement reaction. And so this 2.31 is used for both this reaction and this reaction. Sodium bromide plus silver nitrate yields silver bromide plus sodium nitrate. And you might go, you know, out of that 2.31 grams, how much was required for the sodium chloride and how much was required for the sodium bromide? You might be thinking that. But it's a unique amount and we can figure it out. And so this is how you figure it out. I don't know how much is required for each one. And this is the combined. So this is multiple unknown problem. Multiple unknown. I need X grams to react with the sodium chloride, and I need Y grams to react with the silver nitrate. And so 2.31 grams is equal to X grams plus Y grams. And so how am I going to do stoichiometry here? Like this. Well, let me tell you how I do it here. This is an unknown mixture. There are different methods. I like the, this is the graphical visual method. Okay, well, we're going to do assume mixture is 100% sodium chloride. If the mixture is 100% 100% sodium chloride, then what that means is I have 1.001 grams of sodium chloride. Then it's easy. I'll go from grams of sodium chloride to moles of sodium chloride. Actually, I don't want to calculate the molar mass, although it's probably not hard. I'll just look it up. NaCl. 60.66. Wait, no, that's not it. 5844. 5844 is its molar mass. So 1 mole of sodium chloride, 5844. From Wikipedia. And what's a mole ratio? It's a 1-to-1 mole ratio. So 1 mole of silver nitrate for every 1 mole of sodium chloride. And then what's the molar mass of silver nitrate? $169.87. 169.87 grams of silver nitrate per mole. Silver nitrate. many grams of silver nitrate? So if that were 100% sodium chloride, 1001 divided by 58.44 times 169.87, then that requires 2.9096 grams of silver nitrate required. But it only required 2.31 grams, so it's impossible. It cannot be 100% sodium chloride. Well, let's assume mixture is 100% sodium bromide. And so all 1.001 grams would be sodium bromide, like that. And then let's take a look. Let me get the molar mass of sodium bromide. 102.89. 1 mole, 102.89. Then it's a 1-to-1 mole ratio. And then 169.87 grams of silver nitrate per mole. Silver nitrate. So 1001 divided by 102.89 times 169.87, 1.65. So if this mixture were 100% sodium bromide, it would only require 1.65 to 6 grams of silver nitrate required. Well, we required 2.31, and so it cannot be 100% sodium bromide. So C, we're going to graph the relationship. This is what I call the graphical visual method. We're going to graph it. We're going to graph it based on percent sodium chloride. We're going to go to 100%. Over here, we're going to put grams of silver nitrate. Here. It doesn't matter. I could have done it the other way too. I think I should do it the other way. This is X. I'm going to graph it the other way. Sorry. I'm going to put percent sodium chloride on this 100%. We got 0%. So if we have 0% sodium chloride, it's 0% sodium chloride means we have 100% sodium bromide, and we require 1.65 grams. Put that here, 1.65 grams. This is grams of silver nitrate required. So that's our first data point. At 0% sodium chloride, we need 1.65 grams. At 100% sodium chloride, we're going to need 2.9 grams, 2.91 grams. We'll go here, we'll go 2.91 grams. There. And so this is the relationship here. This is a linear relationship of y is equal to mx plus b. So we're going to get an equation. The equation is going to be this. Y is the percent sodium chloride. So the percent sodium chloride is equal to M, the slope. The slope is going to be delta y. Delta y is 100%, 100 minus 0, over delta x. Delta x is 291 minus 165, 2.91 minus 1.65. 1.26. 0.26 times X. X is the grams of silver nitrate required, plus B, the slope, the intercept is 0. The intercept is 0. No, actually, the intercept's not 0, is it? It is. And so let's try to figure out this. Here, what's going on? Is that right? Well, let's do a quick test here. A quick test is if it's 291 grams of silver nitrate. So if it's 291, oh no, 165 is the intercept. Let me just try it. 2.91 times 100. Divided by 1.26. Now the intercept is going to be tricky. So when X is equal to 0, what is Y? I didn't do it. I don't have the proper intercept. It's going to be negative. And I'm going to figure it out. And so I could figure it out because 291 minus 126. $165. 65. So it's going to be minus 165. Okay. Minus 165. And so I figure out a line. We could do a couple of tests really quick here, just to see, does it work? And so if I have grams of silver nitrate and I'm calculating out percent chloride, so if I do this, let me see if I got it. Maybe I don't. 2.91 times 100 divided by 1.26 minus, well, actually, let's see what it equals. 230. No, it's actually 130. 130%. Well, the intercept is actually minus 130. And then it works. But I just have the graphing is a little bit more complex because the intercept is a little harder to find. I didn't graph it far enough out. I could have graphed it far enough out. Usually I just use Excel to do this. And so let me use Excel to do this, and then we could get the intercept quickly rather than graphing it by hand. I would have graphed it by Excel. And so I'm going to do that quickly. Otherwise, I was coming up with some mathematical tricks to get the intercept, which is when X is equal to 0. And so on the Y, we had percent sodium chloride. On the X, we had 1.65. If we had 1.65, we had 0% sodium chloride. And then if we had 2.91, we had 100% sodium chloride. And so this was the grams of silver nitrate. And this was the percent NaCl. Here. All right. Okay, now to graph this, we could just highlight these. What's going on here? Okay, and then I'm going to insert a chart, scatter chart, like that. 2.91, 100, 0. Something's off with my chart. I don't know what's going on there. Very bizarre. Very, very bizarre. What's going on with my charting? Well, I'm having trouble with my data. 0, 100. It's doing this in rows. That's really weird. I want it done in columns. And so it's picking this first one. This as X. This is right now, but something's wrong with my Excel, the formatting on my Excel. It's not right. So anyway, this is the equation here for the line. And so if I want the percent sodium chloride, I just have to add in an X value here. And the X value is how many grams of silver nitrate I used. And so it varies. The grams of silver nitrate varies from 1.65 here all the way up to 2.91. At 1.65 grams of silver nitrate, we have 0% sodium chloride. At 2.91 grams of silver nitrate, we have 100% sodium chloride. And so how many grams did I actually use in that particular problem? How many grams I actually used in that setup? I need to go to the whiteboard. Oh, actually, you guys can't see this, can you? Sorry. Well, I used 2.31. And so, here you go. So I actually used 2.31, which is around here. 2.31 means I have, about 50% sodium chloride, but we can plug that in here. X for X. And so Y is the percent sodium chloride. we'll plug that here. That's equal to 79.365. 79.365 times X, which is grams of silver nitrate, 2.31 grams of silver nitrate required. So let me go back. It was 2.31. And then the intercept, which is minus 130.95. All right, so let's go ahead and calculate it. 79.365, which is the slope, times 2.31 equals minus 130.95. 52%. So, you know, it was around 50%. So percent sodium chloride comes out to 52.38% sodium chloride. And so it depends on how many grams of silver nitrate you use. From that, you can tell how much percent sodium chloride there is. The more grams you use, the higher the percent sodium chloride. The fewer grams you use, the lower the percent sodium chloride. Like this, sodium chloride requires more grams to react than sodium bromide. Sodium bromide only requires 1.65 if it were pure, and the sodium chloride would require 2.9 if it were pure. So let me just go to the point of this. The point of this is, you know, point of this is based on how many grams of silver nitrate we use total, that is X and Y. This is two unknowns. X is an unknown and Y is an unknown. Based on this total, we can get a unique percentage of these here, because each of these uses a different amount. And so the total will be unique. And so the total tells us exactly how much sodium chloride and sodium bromide is, the X plus Y. And you might think, well, it's not possible because we have, you know, two unknowns here. And so that's one way of solving it, is a two unknown problem. So this would be an advanced problem for Chem 1A. In fact, this problem is like in chapter 1 or chapter 2 of Chem 1A. It's a problem similar to this is, okay. All right, anyway, let's move on here. We got to move on. I'm behind, so that was, but stoichiometry is really an important topic in chemistry. And so that's why I spent so much time going through all the problems of stoichiometry. Let's take a look at the next chapter here, and let me show you. No, not the screen. Okay, so the next chapter is chapter 11. Make sure I'm still recording. Yeah. Well, let's take a look at chapter 11. I got to log down. Yeah. Atomic theory. Oh, so we already did atomic theory part 1. This is atomic theory part 2. The quantum model of the atom. From atomic theory part 1, you know, what makes the element unique? What makes the element unique are the number of protons, you know. All atoms of an element have the same number of protons. And different elements are different because they have a different number of protons, and their chemical properties are going to be different. And so how does the number of protons correlate with chemical properties? We want to understand chemical properties based on the number of protons, and the pattern is very difficult, to see. And so there's something missing there. And what we're going to look at is not atomic theory. We're going to look at quantum theory, quantum mechanics. As atoms, people believe in atoms now. There's plenty of proof for that. And atomic theory, we need to understand more in depth. And so this is part of atomic theory, which is pretty much the theory of chemistry. In other words, here, chemistry is based on theory. And what theory is it? Well, the theory is quantum mechanics. Quantum mechanics gives a more fundamental description of what's going on with atoms, what's going on with the properties of atoms, molecules, whatnot. In other words, this is the theory that underlies chemistry. So if we want to understand chemistry, we need to understand quantum mechanics or quantum theory, quantum. Or quantum chemistry. It's given a lot of different names: quantum mechanics, quantum chemistry, quantum physics. It's all the same thing. Quantum mechanics, quantum chemistry, quantum physics. All the same. Chemistry is based on theory. What theory? Chemistry is based on what theory? The answer, quantum mechanics. Quantum mechanics. The theory that underlies chemistry is quantum mechanics. So let's look at the development of quantum mechanics right now. And this chapter is pretty much the development of quantum mechanics, and then some the key. A lot of theories, following the scientific method, a lot of theories originate from observation. And so we got observation, and then some patterns, trends, laws, to hypotheses, theory. And the theory here, quantum theory, where did it come from? Quantum theory came from observations of unusual light patterns. Unusual light patterns. Unusual light patterns. Well, these are patterns. And from these patterns, they could get mathematical, what we call empirical equations, empirical mathematical equations that can describe those. So we get things like the Rydberg law, etc. And then came a hypothesis about energy, and quantized. And then we came up with quantum mechanics. Quantum theory is the second one. The first theory that came about was Bohr theory, B-O-H-R, Bohr theory. But Bohr theory turned out to be proven wrong. Not 100% of it was wrong, but a lot of it was wrong. And so this led to, quantum physics. The unusual light patterns, why were these unusual? Because these were not predicted were not predicted by Newtonian physics. Newtonian physics. Newtonian physics is Isaac Newton, you know, the guy who got the apple on his head. Newtonian physics is called classical physics. Classical physics. And so up to this point, you know, before quantum mechanics, you know, classical physics is still in use. Classical physics could get people, you know, to the moon and back. You know, classical physicists didn't see this quantum stuff because usually it affects, you know, very small things. These unusual light patterns was the first to say maybe classical physics is not comprehensive. It's missing something. And so do that. Well, what were the unusual light patterns? Well, when we think about light, when we think about sunlight, you know, where does sunlight come from? Well, sunlight comes from the sun, yeah, but that's, you know, the circular. Sunlight does come from the sun, but where does the sunlight come from in the sun? Do you know? How is sunlight generated? If you think about the sun is one gigantic light bulb. And so how does it work? How does the sun work? It's a gigantic light bulb. The sun is just one gigantic fireball. People in the old days, they would have flames for light, you know, would burn things like whale oil lamp, something like that. But in that fireball, you have a plasma, and in that plasma, you got electrons and atoms and ions. You know, the atoms in that fireball are moving so fast that they collide and knock electrons off the atoms. So you got free electrons and you got ions. A plasma, well, what a plasma is a plasma is a partially ionized gas. You know, it's an ionized gas. That is, the gas particles undergo severe collisions, knocking electrons off, creating ions. And it's those electrons that we're interested in, because the electrons have high kinetic energy and they get excited. But the electrons don't stay excited forever. So eventually the electrons are going to drop back down in energy. As they drop back down in energy, they start to emit light. And so what we see in sunlight is we see all the colors of the rainbow. We see white light. You know what white light is? White light consists of all the colors in the rainbow. What are all the colors in the rainbow? Well, you should know this. It's Roy G. Bibb. It's what we call the complete visible spectrum. The complete visible spectrum starts off at red, and we have different energies of red light. And then it goes to orange, yellow, green, blue, indigo, and violet. And so we have all the colors of the rainbow. It turns out in terms of energy, red is low energy. Low energy. Violet is high energy. We could have lower energies than red, which we call infrared. Infrared IR. And we could have higher energies than violet, which we call ultraviolet. And so we could have infrared and ultraviolet, but we can't see those. And so infrared is even lower in energy than red light. And ultraviolet is higher in energy than violet light, ultraviolet, and infrared. And what happens is these electrons in the sun, sometimes they aren't excited so much. So when they aren't excited so much, so when they drop down, they emit infrared light, infrared radiation. You feel it as heat. If they get excited a little more, they start to emit red light. A little more orange, yellow, green, blue, indigo, violet. So, so basically what that means is we can make a light bulb out of anything with electrons, you know, as long as we can excite the electrons, we can make a light bulb out of anything with electrons. So let's take a look. Actually, I saw a great one with the ethanol. Liquid oxygen rocket engine. What was that? That NASA one. What was the other one? This one. Look at this. Okay. Keep an eye on this thing. Do you think this thing, this cone here is hot right now? I think it's hot, but you can't see it that it's hot, can you? This cone is probably aluminum oxide or something like that. But you know, if you put your hand, if I put my hand next to the cone, I don't want to touch it because it'll probably get third-degree burns. But if I put my hand, I could feel the infrared radiation hitting my hand because you feel the warmth of that cone hitting your hand. That's infrared. So what's happening is there are electrons in the ceramic. Those electrons are getting excited and they don't stay excited forever. Those electrons get excited and then they drop down in energy. And when they drop down in energy, they'll emit infrared radiation and you feel it in your hand. Infrared's kind of low energy. Now it's starting to glow. And so now it's getting a lot more excited because now it's going to start emitting red light. When it starts emitting red light, well, that means electrons are getting excited more. When they get excited more, they'll drop down, they'll emit higher energy, what we call radiation, light. And so now you can see it. Not only can you feel the infrared, but you can see the red light coming off here. So it's starting to glow. Orange, yellow. We don't really see, because it's starting to mix. When you start mixing the colors, you aren't going to see the green. It's going to be green mixed with red, orange, and yellow. Green mixed with red, orange, and yellow is going to look like this. Blue is going to be mixed in there, indigo, violet. All right, now this is good. Now do you see we got white light? When you mix all the colors of the rainbow, it looks white. And so this is a light bulb. You know, this is probably not a very practical light bulb. You wouldn't want to be using this for your reading lamp next to your bed because you have this ethanol rocket engine blasting. And it's taking a lot of energy just to make that, you know, not that much light there. You know, but this is a light bulb here. And so we could make a light bulb out of this ceramic here as long as we get it hot enough, as long as we get it excited enough. That's what's happening in the sun. So essentially what we can do is we can make a light bulb out of anything. Now, before LED light bulbs came out, there was the, okay, question. Was there a question? Sorry. Oh, okay. Vanessa, do you have a question?
No, I don't.
Oh, okay. All right, that's fine. Okay, so basically in the old days, we had tungsten light bulbs, you know, like Thomas Edison and that. And so we got this ceramic here. So this is making a pretty cool light bulb. Let's see how bright it gets. Wow, there we go. Some light. And so let's look at the old, like, what is it, Edison light bulb. Oh, Home Depot. Edison light bulbs. What is that? All right, these are the old stuff. Are these LEDs? What is this? That's LED. These are make-believe. That's pretty cool, kind of fake tungsten light bulbs. Vintage. Well, that's fine. Okay, these aren't LEDs. This is vintage. This is a vintage. They make these LED ones that look vintage. That's pretty cool. What are the vintage ones here? This is called incandescent light bulb. So when we look at it, it's a piece of wire. And you want a piece of wire, one, that's cheap, right? And two, that has a very high melting point. Well, you know, platinum has a very high melting point. You can make an excellent light bulb out of platinum, but it's not cheap. Gold too. So you need a piece of wire. Why wire? Because wire has electrons. And so tungsten is cheap. Tungsten has a very high melting point. Tungsten is the element W. And so they use tungsten. There's a piece of tungsten wire in here. But there's one serious problem with tungsten. The serious problem with tungsten is it's easily oxidized. And if tungsten becomes oxidized, it turns into ceramic, and the ceramic becomes very brittle and falls apart. And so what we need to here is we need to prevent oxidation. Well, how do you prevent oxidation? Because we live in an oxidizing atmosphere. Air is 20% oxygen. And so what we have to do here is we have to put in here an inert gas. Inert gas like this would be like nitrogen, you know. Nitrogen would be inert. Nitrogen's not gonna, it might form a tungsten nitride. I've got to worry about nitride. Let me see. If tungsten nitride is a possibility, but let's see how easy it is to make tungsten nitride. Because, you know, nitrogen can also act as an oxidizer. It's just not as good of an oxidizer as yeah. Maybe we don't want to use nitrogen. Probably don't want to use nitrogen. So what other inert gases? Well, there are inert just means it won't react in this particular reaction. It could react in other reactions like the Haber process or whatever. But we could use other gases like argon. You know, argon's a Nobel gas. And so what gas do they use here? You know, you want a cheap gas, right? And an unreactive gas. And so let's see, what gas is used in incandescent light bulbs? Oh, I guess it's argon. Argon's not so cheap. I use argon. I used to use lots and lots of argon. Most of the gas I use is argon. Very unreactive. Nitrogen is much cheaper. And so if I could get away with nitrogen, I use nitrogen because it was so much cheaper than argon. Krypton's expensive. Didn't use krypton. Helium is okay, but the problem with helium is it'll leak out so easily, you know, out of the bulb. Argon is slow to leak out of the bulb. Whatever you do, you don't want any oxygen in there, because if you have oxygen, it's going to oxidize immediately. And that is, if you break the bulb and then try to use it, you'll oxidize it in a second, and the filament will break. And so it looks like it's mostly argon with a little bit of nitrogen. Well, a little bit of nitrogen probably isn't so bad for forming nitrides here. Okay, then what do? They pass electricity through this. When they pass electricity, that's like the flame, you know, it's getting the electrons excited. As the electrons get excited, they get a little bit excited, you'll feel the infrared. More excited, red, orange, yellow, green, blue, indigo, violet, and eventually once they're excited enough, it's white light, like it's emitted. It's white light. And so this is all predicted by classical physics. You know, classical physics, we predict. We can make a light bulb out of anything. With electrons, you just excite the electrons and that's fine. Have you ever seen a lightning bolt? Obviously, you've seen a lightning bolt. What color is a lightning bolt? Yeah, it depends, but it's white. Yeah, it's white. Why? Because lightning bolts consist of very excited electrons, right? So what if you can make it like a controlled lightning bolt? You know, not an out of control lightning bolt like you see, but a controlled lightning bolt. How do you make a controlled lightning bolt? A lightning bolt is like jagged like this. A lightning bolt is jagged like this because there's a lot of gas particles and there are collisions and that kind of stuff. But what you can do is you can make a vacuum. If you have a vacuum that is not many gas particles, then the lightning bolt can go straight rather than colliding back and forth like a ping pong ball, you know. And so what you do is you can make a controlled lightning bolt. And so this is what people try to do with a gas lamp, you know, with a gas lamp like this. And so it's like, you know, the sun's a gas, you know. We see, but we don't see, you know, that kind of, we just see the product, the radiation of light, you know, here. And so what came up was the idea to make a light bulb out of hydrogen gas, you know. And so we should be able to make a light bulb out of hydrogen gas and it should give us white light. That's what was predicted by classical physics. Hydrogen gas light bulb. So this is it. This is your hydrogen gas light bulb. And so what you're doing is you're taking a tube of hydrogen gas, but you don't have it too concentrated. If you have too much gas in there, then you're going to get jagged, like a kind of a light bulb, lightning thing. But here, if you have it as low pressure, this is low pressure hydrogen gas. If you have low pressure hydrogen gas, this is the light bulb that you get. And so what you essentially do is you essentially have a lightning bolt go through here. The lightning bolt is like tens of thousands of volts. But if you have a low pressure, then you only need about 5,000 volts of electricity. You put in 5,000 volts of electricity, you get what we call a discharge, you know, electrical discharge, and we get that. But, you know, the problem with this is it doesn't look white, you know. So you crank up the power, you know, you crank up the power to get the electrons really excited and nothing happens. It just becomes brighter. It becomes brighter, but it doesn't become white. You know, they're expecting white light to come from this, like exciting some electrons here and some up here, and eventually we'll have the full spectrum of colors. We'll have all the colors of the rainbow. It turns out we didn't get all the colors of the rainbow. This should have given us white light, because what does hydrogen atom consist of? Hydrogen atom consists of, we're looking at atomic hydrogen right now. because in this discharge, there's a lot of energy. That energy is going to break up the hydrogen molecules. The H2 molecules get broken up into hydrogen atoms, and the hydrogen atoms themselves get excited. Well, what does a hydrogen atom consist of? A hydrogen atom consists of a proton and an electron. Now, that electron could be excited to any, and so an analogy would be speed. You know, the electron could go any speed it wants. It could go slow, it could go fast, you know, depending on how much energy it has. And so this should start off going red. It doesn't. And then yellow, orange, green, etc., and get wider and wider like that. But it didn't. In fact, when they analyze the colors of the rainbow, you know, you can pass white light through a prism. When you pass white light through a prism, you can see the colors it's made of. And so let's look at the, let's look at that prism. So when we pass white light through a prism, we get all the colors of the rainbow. Just the prism will just spread out all the colors so we can see them. Yeah. Here, although this is kind of weird. This one's going this way. It's going another way. Let's get a real one. Do we have a real one? Yeah. Okay. So all the colors: red, orange, yellow, green, blue, indigo, violet. One way people remember this is the acronym Roy G. Biv. Roy G. Biv, the colors of the rainbow. Okay. Now, when they did the hydrogen lamp through the prism, they didn't get that. When they threw the hydrogen lamp, here's the hydrogen lamp. Well, one thing is, it sure doesn't look white. Although it looks white here, it isn't. It's more purple. You can see the purple color on the background there from that. Okay, this is not working. I'm trying to shrink it down. Okay, there it did. Okay, so they're passing it through the prism here. And they don't see all the colors. In fact, they only see 4 colors. They have this one red. Red's actually a range. The range of red, and they can characterize the light by something called the wavelength. This is the wavelength here. And it starts at 760. Beyond 760 is what we call infrared. And so this is backwards from the way I wrote it. Red's over here on the right, violet's on the left. Violet ends at 390 nanometers. And so there's a range of red colors all the way from 760 until it starts to blend into orange, you know. And so 656 is one specific color of red. And we don't see any of the other reds, nor do we see any orange. There's no orange, there's no yellow. And then finally, a lot of green is missing, but there's this one green at 486. And then there's only one blue at 434 and one violet at 410. And so there are only these 4 lines of color. What happened to the rest of the rainbow? I'll show you. The rest of the rainbow would look like this. Let's look at what the solar spectrum looks like. The sun is a gigantic hydrogen lamp, right? And so we're making a mini hydrogen lamp here to mimic the sun's gigantic hydrogen lamp. And so if we look at the solar spectrum, the sun consists of hydrogen and helium. So here's your gigantic hydrogen light bulb called the sun. And this is what it kind of looks like. You have all the colors of the red, all the way to violet. There are some black lines here that are missing. These black lines correspond to absorptions due to certain elements you know. And so there are some little gaps here, but it's because oxygen goes in and blocks this color here or that color here for atomic hydrogen, etc. And so this is the solar. Let's see the solar without those absorptions here. Sun spectrum. And so why doesn't the hydrogen lamp look like the sun? The sun is made up of hydrogen. We have a hydrogen lamp. Maybe it's not getting hot enough. No, you crank up the power to get it really hot and still don't see it. And so something weird is going on, you know. And so what's going on? And so that was the unusual observation, the unusual light pattern observation, you know, that led to it. And so the pattern can be fit mathematically. And so let's go. Oddly enough, this pattern fits a mathematical equation called the Rydberg law. So what's a hypothesis? So we have it's a simple law. It's you know, Rydberg law looks like this. The energy, you know, the energy of the light here, the energy is related to the wavelength, you know. Ultraviolet is higher in energy than infrared, and the violet light is higher in energy than red light. And so we'll talk about the energy. But in the Rydberg law, the energy of the light is equal to R sub h, which is called the Rydberg constant, over 1 over n final squared minus 1 over n initial squared. So it's a very simple equation where n is an integer starting with 1, 2, 3, etc. It's the integer value. And so we have this mathematical equation, this empirical equation that fits this pattern. So we can make other predictions. For example, we could use this to predict there's lines, what we call lines in the infrared, and there's lines in the ultraviolet. You can use this equation to predict those things. But, you know, we don't have a good fundamental description of what's happening here. You know, so we want to hypothesize something. And so what was the hypothesis? The hypothesis was this. The hypothesis was the electron here cannot move any speed it wants. It's a weird hypothesis. So think of this like this. Think of it, you're driving a car and you cannot go any speed you want. Let's say from 0 to whatever the max is. You can't go any speed you want. So for example, you can go 0 miles an hour or you could go 25 miles an hour, but you can't go anything in between those two. Or you can go 25 miles an hour and you can go 50 miles an hour, but you can't go any speed in between those. And so that's what they're saying for the electron. The electron can go 25 miles an hour, but it can't go 26. That's forbidden. The next allowed one might be 50 miles an hour. So the electron can go 50 miles an hour, but it can't go anywhere in between. So there are forbidden energies and allowed energies. So that's the hypothesis. The reason we don't see any other colors of red is because those are forbidden. You know? And so forbidden, these are allowed. All the blacked out regions are forbidden. And so these are what we call allowed energies. Allowed energies. And these blacked out areas are called forbidden energies. So what's causing these blacked out areas to be forbidden? Why can't the electron move? In the sun, the electrons are not, these are not forbidden. When we look at the solar spectrum, all those are allowed. So in the sun, the electrons can go any speed they want. Why in the hydrogen atom cannot the electron go any speed it wants? So that was a major problem, because in classical physics, it should. You know, we think, I mean, in classical physics, the way people envision the electron and the nucleus as like a little satellite. And if the satellite has a little more energy, it's going to orbit a little bit farther. If the satellite has less energy, it orbits a little closer. So the orbit depends on how much energy it has. But it can have any energy it wants. You know, it could go slow and close, or it could have high energy and be far, and higher energy, be farther and farther away. So the weird thing is in terms of classical physicists, is this electron can't orbit anywhere it wants. There are allowed orbits and forbidden orbits. Now, what causes an orbit to be forbidden? Why can't the electron just be a little, like 1 millimeter further out? If it's 1 millimeter further out, it's a hair more energy, but that's forbidden. It can't. And so what's causing that to be forbidden was perplexing problem for classical physics at the time, because it just doesn't make sense. It doesn't make sense at all. You know, they were thinking electron as being a particle. You know, it's like a baseball, something. You throw a baseball, you know, it depends on how strong your arm is, but you can throw it from the slowest speed to the highest speed. You can throw it, and anywhere in between, you know. There's nothing forbidden. And so what's forbidding this? It didn't make sense. But it did explain this. If we had forbidden energies here, then that explains why so many areas are blacked out. There's no light, because all those are forbidden. So let's look at light first, a little bit, and then we're going to go to more of the theory and then figure out what's going on. And so light is called electromagnetic radiation. That's light. Probably should have had some PowerPoints, but it's all right here. Bees' eyes, you know, bees' eyes can see ultraviolet. We can't see ultraviolet. It's not visible. Bees can't see red. We can see red, so maybe we got that over bees. In fact, we can only see a small fraction of the electromagnetic spectrum. If we look at the entire electromagnetic spectrum, the visible region is just this small fraction here. And so that's the colors of a rainbow: red over here, all the way to violet over here. This is in terms of energy, you know, is here. This is gamma rays. There's a whole range of energies, a spectrum of energies for gamma rays, and then X-rays. Gamma rays are the highest energy, followed by X-rays, followed by ultraviolet, followed by visible, where we'd have violet all the way to red, and then infrared. And lower energy than infrared is microwaves. You know, a lot of people think microwaves are higher in energy than infrared. No, they're lower in energy. Microwaves are just above radio waves. And for radio waves, we have FM. FM is what we call megahertz. And then we have AM, which is in kilohertz. Hertz is the frequency here. And then long wavelength radio waves here. And so there are three ways we characterize light. One is the frequency, two is the wavelength, and three is the energy. When we look at visible light, we characterize it by this wavelength. The wavelength is the peak-to-peak distance. When we think about light, we think about these oscillating electric fields and oscillating magnetic fields. Light are these oscillating electric fields that are moving very fast. In fact, they're moving at the speed of light. And so light moves at the speed of light. And what you see, let's say a light wave hits you. When a light wave hits you, what you're going to see are oscillating electric fields. Oscillating electric fields means it goes plus, minus, plus, minus, plus, minus, like that. And so it's hitting you plus, minus, plus, minus, plus, minus at the speed of light, which is 3 × 10⁸ meters per second. Very fast. So the waves, these waves are characterized by the wavelength. You know, the wavelength is the peak-to-peak distance here. So radio waves have long wavelengths, you know, long distances between the peaks here. And the wavelength is in meters here. So some of the, like here, it would be like 1,000,000 meters between one peak to the next peak. If you look at FM, it's about 1 meter to 10 meters. And so one meter to 10 meters in between the top of one peak to the top of the next peak, you know, FM. If you look at gamma rays, it's like 10 to the minus 16. Look how many orders of magnitude. That's so many orders of magnitude difference. 10 to the minus 16 is smaller than an atom. You know, atoms are on the order of angstroms, or 10 to the minus 10. And so atoms are about here, 10 to the minus 10. This is way smaller than an atom. This is 1,000,000 times smaller than an atom, is the peak-to-peak distance. Now this thing is moving at the speed of light. And so if it's moving at the speed of light, then we can get something called the hertz. A hertz is a oscillation, one oscillation. So we hit a peak here, and then we go to the valley, and then go back to another peak. So that peak-to-peak oscillation is called a cycle. And a hertz is 1 cycle per second. That would be at 1 hertz, 1 cycle per second. And so over here, we get 1 cycle per second over here at these wavelengths. But when we look at a megahertz, like FM radio, megahertz is 1,000,000 cycles per second. And so 1 second, we have 1,000,000 peak to peaks pass us. And then we can get some insane number here, 10 to the 24th peak to peak cycles, oscillations in a second. 10 to the 24th, you can't even count that. It's so high frequency. The frequencies in hertz. Hertz is a cycle per second. So because the wavelength is so short and it's moving so fast, light is. But anyway, we're out of time. So I'm going to stop here, and then tomorrow you'll have to be a little patient. We'll see how it works out, because nobody is at school. And so all the equipment has been put away. So I've been looking for it. I was looking for it today. So I got to sort through it. But tomorrow we're going to do lab. I got to do a little bit of catch up though for lecture too. So the lab is not so long tomorrow, but we'll see how it goes. All right. Anyway, thanks. See you guys tomorrow. Let's see. Okay, yeah. You know, I haven't graded things. I'm behind on the grading on the quizzes. So I'll post those grades. As long as you turned it in, you're fine. And the exams, I'm gonna work through the exams tonight, and I'll try to get those back to you tomorrow or at the latest Friday. And then today's quiz, yeah, uploaded. I'm gonna post a link on Canvas for today's quiz. And then I'm going to talk about the last problem on the test tomorrow, probably. I know there was a question about that Monday. Okay. The quiz was the, what was the quiz? Was the problem? Yeah, Moniz, I'll post the quiz question on Piazza. You can turn that in later if you want. Okay. All right. So yeah, I'll upload a link on Canvas right now, and then I'll post the quiz question on Piazza, and then tomorrow we're going to be doing a little catch up and lab. So lab, if you have a lab notebook, that's good. If not, that's okay. Talk about lab tomorrow. So tomorrow I'm going to go to school, and then we'll see how it goes. Okay. All right, thanks guys. See you tomorrow then.